Tonight's presentation is When Data Doesn't Look Right. Our presenter, Mike Bush. Mike is president of Savvy Aviation Incorporated, author for numerous aviation pubs, and certified flight instructor, certificate holder, A&P mechanic with IA privileges, aviation maintenance technician of the year way back in 2008, and of course a member of EAA. Mike, thank you so much for being with us and volunteering your time, continuing in your series of monthly webinars with us. We sure do appreciate you and all you do for EAA webinars, and everybody tuned in for sharing your information with us so we can hopefully be more knowledgeable aircraft owners and maintainers. Mike, I'm going to turn control over to you.
Okay, thanks, Tim. Good evening, everybody. Let's see if I can take over here. I'm really glad to see that we're doing Home Builders Week again. I guess that was something that kind of started as a result of COVID, but I'm glad to see that it's continuing. And I'll be doing a presentation about engines and stuff. I think the last day of Home Builders Week, so looking forward to that. Anyway, the presentation tonight, When Data Doesn't Look Right, is a little bit unusual presentation because I'm going to be telling you about a research project that we're doing called Project Gadfly. Kind of interesting. It's not quite ready for prime time yet, but I just thought it would be interesting to give you a kind of a behind the scenes look at something that we're working on and that I'm pretty excited about. Nowadays, more than half the piston GA fleet, probably well over half of the EAB fleet, is equipped with some sort of recording digital engine monitor. The older ones tend to be pretty primitive. They record EGTs and CHTs and not a whole lot else. More modern ones are connected to lots and lots of sensors. They capture all kinds of things, all kinds of temperatures and pressures and voltages and currents and air data information, altitude, acceleration, even GPS position data. So they capture a tremendous amount about what's going on. And I know a lot of the EAB aircraft now are equipped with Dynon equipment, and the Dynon Skyview is one of the most remarkable systems that we work with, that captures just all kinds of stuff, and it's really a great system. So, a modern engine monitor with a few dozen sensors connected to it, with a 1 second sampling rate, which is kind of typical of these things, records more than 100,000 measurements per hour of flight. That's a lot of data, and this data can be really invaluable for diagnosing problems. In a perfect world, the engine monitors would watch all this data in real time as it's being collected, and would alert us if anything doesn't look right in the data while we're flying in real time. Unfortunately, the current state of the art, even the best engine monitors, the most sophisticated ones, have an extremely limited ability to do this, to alert us to problems. Some engine monitors do have an alarm capability and have the ability to configure various maximums and minimum values for things like CHTs and TITs and oil temperature and so on, where you can program the device to alarm if a particular parameter gets outside of limits that you set. But an awful lot of the engine monitors will only alarm if the parameter reaches the manufacturer's redline value, and they don't allow user configurable alarms. And getting an alarm when you reach red line is generally too late to save the day, so it's not particularly useful. You know, if you're flying a Lycoming engine, you really would like to be alarmed if CHT starts to go up before it gets to 500 degrees, you know. But a lot of the engine monitors are hardwired to manufacturers' red lines as far as their alarm capability is concerned, which is not terribly useful. And still other engine monitors don't have any alarm capabilities at all. So, but even the best ones only provide very simple alarms when a certain parameter exceeds some maximum or minimum value that is either hardwired into the unit or user configurable into the unit. And none of the engine monitors right now do what our human analysts do at Savvy Aviation. We've got a staff of about 10 people who do nothing but look at engine monitor data that's downloaded from these devices and uploaded to our platform. And what the human analysts are trained to do is to look for patterns and correlations among various sensor values, not just to look at individual sensors and see if they exceed certain maximum or minimum values, but to look for correlations between the various sensors and to get a big picture that way. So, for example, you know, if analysts notice that cylinder 3 has EGT that differs significantly from the other cylinders, he wants to know if there's a significant divergence in CHT in that cylinder that would confirm that there was some abnormal combustion going on. If the CHT looks normal and the EGT looks abnormal, the chances are it's just a bad EGT sensor or maybe a bad connection in the harness. So we always look for confirmation. If we get one sensor that looks unusual, we look at other sensors to see if they will confirm that that there really is a problem. Or say if cylinder number 1 looks like it's starting to flame out when the pilot leaned the engine for cruise, we want to know more than that. We want to know what the fuel flow was, what the manifold pressure and RPM was, what the other cylinders were doing as the mixture was leaned. So again, we're looking at a whole bunch of different sensors and how they correlate with one another. That's what we really need to do to make sense of this data. And none of the engine monitors do anything like that right now. The human analysts do it, but the avionics don't do that, at least at this point. And you know, the problem with the human analysts is, you know, our staff of 10 analysts are literally drowning in data. We've got more than 5 million flights of piston GA aircraft data in our database. We have more than 10,000 new flights every week that are uploaded to the system. And that rate is accelerating. You know, 10 analysts can't possibly examine all of those flights. They can only, you know, look at a small fraction of the flights that are uploaded to the platform. Which flights do they look at? They typically look at flights where the aircraft owner who uploaded the data asks for an analysis, asks that their data be looked at by our staff. And they usually get asked that because the aircraft owner or client believes that there's something wrong, that the engine is performing abnormally, and they're looking to have an expert look at their data to diagnose what the problem might be. You know, maybe the engine hiccuped or started running rough or started to lose power, or maybe they got some alarm that CHT or TAT or oil temperature or something was too high. So that's usually when the client will upload the data and ask us to take a look at it. We'd like to do a better job than that. We'd like to be more proactive and less reactive. We'd like to be able to see things that are wrong, that the aircraft owner doesn't even know are wrong yet. And, we can't possibly have human analysts look at every flight that's uploaded. There are just too many of them. So what we need to do is develop some computer software capable of looking at every flight as it's uploaded to the platform and flagging only the ones where something doesn't look right, where the computer says, one of the analysts really ought to look at this flight. So to go through this massive amount of data that's being uploaded to our system and just pick out the ones that look strange, where it would be worth an analyst's time to take a look at it, even if the aircraft owner hasn't asked for it to be looked at. So that was the challenge that we took on. How can we develop software that looks at these flights as they come in and flags the ones that somebody ought to take a look at? It's an interesting problem. Clearly, it requires some sort of artificial intelligence. And we've been doing a fair amount of work with AI on various other things I've talked to you about in other webinars about our predictive analytics with regard to exhaust valve failure risk and how we have software that uses machine learning to look at data and provide exhaust valve failure risk scores so that we flag cylinders where we think somebody ought to take a look, put a borescope in there and take a look at the valve. But what we're trying to look at here is even more general than that. It's not specific to valves or anything. We just want to figure out a way to flag flights that look weird and that somebody ought to take a look at. So this is the thing we're working on. We call it Project Gadfly. It's our one of the projects that is going on in our skunkworks department right now. It's headed up by my partner Chris Rather, who's a PhD in operations research. We're working with some Google people we're working with some folks up at UC Davis on it, and it's a pretty intense and very interesting project. The name Project Gadfly, GAD, stands for Generalized Anomaly Detection, which is what we're trying to do, is to come up with a very general way of looking at a mass of data and determining whether it looks anomalous or whether it looks normal. So that's what the GAD is for. The FLY is pretty obvious. At any rate, the whole idea is to have some software that looks at every flight that's uploaded to the system and flags the ones that somebody ought to take a look at. Our initial effort in this area, we're focusing on the Cirrus SR-22 for two reasons. First of all, the SR-22s tend to be very well instrumented. They tend to have lots of sensors, so we've got a lot of interesting data to work at. And also, we've got a lot of SR-22 flights in our database, probably about 500,000 flights of SR-22s. So we've got a lot of training data for machine learning, which is really important for something like this. So if Gadfly proves out to work for the SR-22, then our plan is to generalize it to lots of other aircraft makes and models. But we're starting out with the Cirrus SR-22, again, for the two reasons that I mentioned. We've got a lot of SR-22 data, and the airplanes tend to be very well instrumented. So the engine monitor in an SR-22 typically captures on the order of 50 different sensors, captures them once per second, which means 3,600 observations per flight hour of 50 sensors each. So now here's where it gets interesting, and I hope I don't give you guys all a headache as we describing this. But imagine that each of these observations, the 3,600 observations per hour, and an observation consists of readings from 50 different sensors, a bunch of CHTs, a bunch of EDTs, a bunch of other stuff. That we plot these observations from the 50 sensors in 50-dimensional space. Now, I know it's a little hard to visualize 50-dimensional space, but hang in there. So we plot a point for each observation in 50-dimensional space. So for an hour's flight, we wind up with 3,600 points plotted in 50-dimensional space. If we do this for the 500,000 SR-22 flights we have in our system, we'll wind up with roughly 2 billion points plotted in 50-dimensional space. What good is this? And I realize this is a little bit hard to visualize, but it turns out that if we do that, the vast majority of those billions of points that we plotted in 50-dimensional space will be fairly tightly clustered into, I guess, what you'd call a hyperblob, a 50-dimensional blob. And that blob in 50 space represents what a normal SR-22 flight looks like. The edges of the blob will be a little fuzzy. There'll be some outliers that seem to not fall into the blob. But most of those points will be fairly tightly clustered into this 50-dimensional object, this irregular object in 50 space. In the jargon of AI and machine learning, this blob that we've created by feeding 500,000 SR-22 flights worth of data into this system and plotting this 50-dimensional blob, it's known as training data. And the 50 individual sensors that constitute each observation are called features. I don't know why they call them features. That's just a machine learning terminology, and so we wind up calling them features. But a feature is data from some sensor, like CHT for cylinder number 3 is a feature. Okay, so we have this blob in 50 space. Now suppose that somebody uploads a new SR-22 flight to the system. The software will plot each of the observations from this new flight in 50 space and see where it falls relative to this blob that we've created from our historical data. If the observation falls inside the blob, then it's probably normal. If it falls outside the blob, it's probably not normal. If it falls a long way outside the blob, it's probably really abnormal. The further outside the blob it falls, the more likely it is to be indicating that something's wrong. So what we want to do is plot each flight in 50 space and see where the observations are relative to this blob that we've used to train the algorithm. And we wind up calculating an anomaly score for each observation, and ultimately an anomaly score for the whole flight. And if enough anomalous observations come out of the flight that the flight has an anomaly score greater than some threshold, we'll flag the flight as being one that seems to be sufficiently anomalous that somebody ought to take a look at it. And we'll ask one of our human analysts to take a look at it. Now, although what I've described to you is conceptually simple, assuming that you have the ability to visualize a 50-dimensional blob, the devil's in the details. The mathematics of doing this is fairly complicated. And Gadfly does this using a multi-level neural network algorithm that AI folks call deep learning. And we were fortunate enough to be able to work with a machine learning engineer at Google named John Sipple, who happens to be a GA aircraft owner and is kind of interested in what we're doing. And he made available this neural network machine learning model that Google developed and is open source that we're using as the basis for how we do this. Okay, now, I've described something to you kind of in the abstract, and I understand it's a little hard to visualize 50-dimensional blobs, but most of us can visualize things in 3-dimensional space. So I wanted to offer you an oversimplified version of what we're doing, but just do it in 3 space instead of 50 space, so you can kind of visualize what we're talking about. So I'm going to pick 3 features instead of the 50 features that we're actually dealing with in the Cirrus. 3 pieces of data that constitute each observation instead of 50. So we can plot it in 3 space instead of plotting it in 50 space. And for the purpose of this oversimplified exercise, we're going to choose the following 3 features: CHT of cylinder number 2, EGT of cylinder number 2, and manifold pressure. And actually, to make this work a little bit better, instead of using the raw CHT and EGT data, we'll normalize it by, for CHT2, subtracting the average of the other 5 CHTs. So we'll come up with something called CHT2 diff, which represents the difference between CHT2 and the other 5 cylinders. So it kind of gives us an indication of how different CHT2 is from the other cylinders. So we'll do the same thing for EGT2 and call it EGT2 diff. So we're going to create a 3-dimensional blob with these 3 features: CHT2 diff, EGT2 diff, and manifold pressure. And we did this. We didn't do this for 500,000 flights. We did it with several thousand flights, but I just wanted to give you the idea. And so here's what the blob looks like, okay, in 3 space. This is a 3-dimensional plot where forward and back is manifold pressure, up and down is CHT2 diff, and left and right is EGT2 diff in 3 space. And here's our blob. And we actually color coded the dots as we plotted them in 3 space, so that the orange points are the things that observations that were taken during the takeoff and climb phase of the flight, the blue dots in the cruise phase of the flight, and the descent and landing in the green dots are the descent and landing phase of the flight. So of course, the takeoff and climb are closer to the front because they're high manifold pressure, and manifold pressure is in the front back axis here. And the descent and landing are kind of in the back because they have low manifold pressure. And the cruise dots are in the middle. But as you can see, they fall into a fairly well-defined, a little bit fuzzy blob. It turns out that the more sensors you have and the higher dimension you plot this stuff in, the crisper the blob is. In 3 dimensions, it's more fuzzy than it is in 50 dimensions. And there's actually a mathematical theorem that says that. But for the purposes of this discussion, we're just going to do the 3 dimensions, and you can see kind of what the blob looks like. And here it is again. There's the 3 dimensions. Now you'll notice that there's a bunch of points out here, which we plotted in red, that are way outside the blob. They're clearly anomalous points, and they would have very high anomaly scores from the algorithm because they're far outside where the rest of the points are clustered. And so that's kind of what the algorithm is looking for, is looking for points that fall significantly outside the blob. And if there are enough of them in a particular flight, then that flight is going to get kicked out and say, you know, somebody ought to look at this flight. It doesn't look right. Now, the interesting thing is that all of these red points in this particular plot come from one flight. And that flight was a highly anomalous flight, and it generated a whole bunch of points that are way outside the blob. Here's what the flight looked like. Some of you are probably more familiar with reading these charts of engine monitor data, and some of you guys probably aren't. But it's not rocket science. So I'll take you on a quick tour through this flight that generated all those anomalous red points, and you'll get an idea what happened. So the flight starts where EGT comes up because the guy started the engine, and then he taxis out and the cylinders warm up. You can see the CHTs kind of coming up to normal operating temperature. And then it looks like 13 minutes or so after engine start, 12 minutes after engine start, he does a run up. He's in the run up area. Manifold pressure and RPM and fuel flow come up briefly, and then they go back down. This is where he did his pre-flight run up. And then he applies takeoff power. And you can see manifold pressure and RPM come up, fuel flow comes up. In the lower trace there, the red line is altitude, and it starts down at airport level. And then he starts to climb. He actually gets up to looks like about 3,500 feet before he stops climbing and starts descending. And there's a good reason that he stopped climbing and started to descend, because something really bad happened. The CHT on the number 2 cylinder just started to run away. All of the cylinders during the climb were at CHTs in generally around mid 300s, 360, something like that. And CHT number 2 went berserk. It started climbing. It passed that red line that is set at 400 degrees, where an alarm should have gone off. It kept climbing, and it peaked out at roughly 600 degrees Fahrenheit before it came back down again. Here's a close-up of what that looked like. It happened pretty rapidly. From the time that CHT2 exceeded 400 degrees, where an alarm theoretically should have gone off, to the time it peaked out at 600 degrees, took 2 minutes. This entire anomalous event from start to finish took about 5 minutes total. Now, the bottom thing there is what we call the Project Gadfly heat map. It's a color bar that represents the anomaly score that the Gadfly algorithm assigned to each observation. Green represents low anomaly scores. Red represents very high anomaly scores. So the portion of the flight that the Gadfly algorithm identified as having very high anomaly scores, that area from about 15 and a half minutes after engine start up to maybe 21 minutes after engine start. You can see that corresponds precisely with where the thermal runaway happened. Now, what happened here? Well, the only thing that can cause a thermal runaway like that is either very heavy detonation or pre-ignition. And I suspect it was a pre-ignition event because it got up to 600 degrees was probably self-correcting, because when CHT gets up to 600 degrees, the corners of the piston start melting and molten aluminum starts getting into the ring grooves and seizing the compression rings and pretty much shutting down the cylinder. So this tends to be a self-correcting situation, but it winds up with a very rough running engine because one of the cylinders is basically put out of commission by an event like this. But you can see that the gadfly algorithm identified the portion of the flight that was anomalous. And keep in mind that gadfly doesn't know anything about detonation or pre-ignition or anything. It's not trained to look for any specific thing. It's just trained to look for things that look different than what most SR-22 flights look like. And it identified this 5-minute portion of this particular flight as being highly anomalous. So this is a flight that it would definitely kick out and say somebody needs to take a look at this and see what happened. You know, looking at the chart, you can see that the pilot failed to take corrective action quickly enough to save the cylinder. You know, if CHT passes 400 degrees and is rising rapidly, you need to act immediately to stop the thermal runaway in order to prevent the cylinder from being severely damaged. Actually, the piston is usually what gets severely damaged. It takes the brunt of this sort of thing. And the pilot didn't take corrective action quickly enough to halt the thermal runaway, and the CHT got all the way up to 600 degrees. So either the engine monitor didn't alarm and didn't give him a warning, or it did alarm, but he didn't respond quickly enough with an appropriate action to stop the thermal runaway. The appropriate action is to go full rich, turn the boost pump on, and throttle back and stop the thermal runaway before it gets to the point where it starts melting things. That didn't happen. So for some reason, the pilot either didn't get an alarm or didn't react to an alarm quickly enough. It's a little hard to tell. Can't tell from the data what the pilot knew and when he knew it. You can just tell what happened. But in any case, it appears that for whatever reason, the pilot was oblivious to the destructive abnormal combustion event that was going on in cylinder number 2 until it got to the point where the engine started losing power and running very rough because it was essentially a 5-cylinder engine. You know, this gadfly research project that we're doing is very interesting. It's our second venture really into applying modern artificial intelligence and machine learning technology to analyzing data from engine monitors and piston and aircraft. Our first venture was FEVA, the failing exhaust valve analytics, which we've been doing now for several years. And we provide our clients with machine learning based exhaust valve risk scores. And we know from experience that if the algorithm assigns an above average risk score to a particular cylinder, it has about 5 times higher likelihood of having a failing exhaust valve than a cylinder with a normal score. We can't tell if the valve is failing from the data. We can just tell that it has a higher probability of being in failure. So when we send out a FEVA report to one of our clients and it shows up an above average risk score for a cylinder, our suggestion is to have the client get a bore scope inspection done of that cylinder as soon as possible, next oil change or maybe even earlier. No guarantee that they're going to find anything wrong, but there's a much higher probability that they'll find something wrong than in an average cylinder. So this whole FIVA thing was our first venture into artificial intelligence and machine learning applied to engine monitor data, and it's been quite a successful program. It's been deployed now for quite some time. And Gadfly is our second big venture in this area, and it's much more ambitious because instead of focusing on a particular kind of failure, it's trying to do very generalized anomaly detection. So our hope is that once we deploy Gadfly, we'll be able to detect problems in our clients' data that they don't know that they have, and we will be able to alert them in a proactive way, in the same way that with FIVA we alert them in a proactive way that there's a high risk of an exhaust valve failure. Gadfly is a much more generalized approach to trying to do the same thing and being proactive. Now, the dream is someday, I don't know if it will happen, I don't know how long it would take, that this sort of machine learning, artificial intelligence, multi-sensor analysis capability would be built right into our avionics so that it can watch the data as it comes in real time and alert us as pilots in real time when something looks like it's abnormal. Just imagine that you could have an engine monitor that was trained on thousands or tens of thousands or hundreds of thousands of flights of that particular make and model aircraft, so that it's trained to know what looks normal and what doesn't look normal. And then as you fly, it keeps an eye on how you fly your airplane, and it uses that to enhance its training. So eventually, the alarms will become more customized to the way you actually fly your particular aircraft. To me, that's a very exciting concept. How soon it'll happen, I don't know. I would expect that it would happen sooner with experimental avionics than it will with certified avionics, because in certified avionics, the FAA has to approve all of the software, and in the experimental world, that's not necessary. So I would expect that this is the kind of thing that would come to the experimental world more quickly than it would in the certificated world. But to me, it's a very exciting concept and something that I hope happens. So, Garmin and Dynon, are you listening? We would love to work with companies like that to try to move this sort of technology from the ground into the cockpit, which is where I think it ultimately belongs. And with that, Tim, that's about all I had to talk about. I'm pretty excited about this stuff, but it's still in its infancy. But I think it's got a lot of potential, and I'd be glad to try to answer any questions. I'm not the artificial intelligence guru, so I might not have answers. But if I don't, I can go get them.
All right, Mike, we do have some questions that have come in. Amazing, just remarkable what you're pursuing there. Thank you very much for doing that. I can see good benefits down the road. John was wondering, how do you develop a baseline data for a given make and model, or serial number? Is it by region of a country? Even more, how do you validate your make and model nominal baselines?
Well, I'm not exactly sure what he's getting at, but basically as I said, we have a very large amount of historical engine monitor data in our database now, about 5 million flights, and about 500,000 of them are Cirrus SR-22s. And so that's a lot of really good training data. Now, a very small percentage of that data is going to be anomalous. Not all of it is going to be normal, but the amount of it that's anomalous is so small that it doesn't really materially affect the blob. It makes the edges a little more fuzzy, maybe, but you train the algorithm by essentially creating this mathematical blob in hyperspace, and that's the baseline. Um, we don't try to tell it anything that we know about SR22s. We just feed it a whole bunch of real life SR22 data and let it figure it out. That's the essence of machine learning, is that you don't try to write an algorithm to solve the problem. You just throw a whole lot of data at the computer and let it figure it out. That's the beauty of machine learning. And for things like this, the machine learning approach is a whole lot better than any kind of a expert approach where you try to use your knowledge of the make and model to try to tell the computer what's normal or not. And the whole idea here is the computer learns what's normal and what isn't normal by looking at a lot of data.
Nayar was just wondering, how soon would a project like this come to life?
Well, that's a good question. I mean, I expect that we're going to be able to deploy it for SR22s pretty soon. We're limiting it to a fairly narrow set of aircraft that right now we're doing it only for normally aspirated SR22s. The turbocharged ones will have a somewhat different shaped blob, and so we want to train the algorithm on a fairly homogeneous set of aircraft. But I would expect that we'll be able to deploy this for the SR22, in a matter of a few months, and then we'll start trying to generalize it to other makes and models, and we'll probably start with the ones where we have the most data in our system. We got a lot of RVs, for example, in addition to a lot of Cirruses. So we've got a fair number of Bonanzas in there. So those are all aircraft that'll probably be candidates for doing this once we've got the SR22 stuff deployed to actual clients, and hopefully it'll be working. It'll be doing a decent job. We'll start training additional models for additional aircraft, additional mathematical models for additional aircraft models.
Mm-hmm. Chris was wondering, does the system have a way to identify faulty instrumentation?
Well, obviously, one of the source of anomalous data is when sensors go bad, or connections to sensors go bad, and those produce outliers. And our human analysts are very good at looking at data and determining whether it's something that's real or whether it's something that is an instrumentation issue as opposed to a real issue. We're not actually asking Gadfly to do that. We're not asking it to diagnose the problem. We're only asking it to flag flights that warrant human analysis. So it's a fairly limited goal, but it's a really important goal, because we would like to know of all the 10,000 flights a week that are getting uploaded to our system, which 50 of them are worth our analysts taking a hard look at and getting in touch with the aircraft owner and saying, hey, we think you got an issue here.
David wonders how much data must be collected before you have confidence that the machine learning is not coming to the wrong center.
I'm not sure the wrong center. I don't know what that means exactly.
Okay.
I mean, the validation of the algorithm will be that it's gonna kick out a bunch of flights that it thinks are anomalous, or analysts are gonna look at them, and if a lot of them they look at and say, I don't see anything wrong with this, then we know we've got a problem with the algorithm. But I don't think that's going to happen. I think there's going to be not a whole lot of false positives come out of this algorithm. I think the real question is how many false negatives are there going to, is it going to miss a lot of stuff? That's what I'm really interested in finding out. And that'll just come with experience when we start using it to look at actual flights as they come in. We'll see how well it does. But I'm reasonably optimistic about it.
Mike, you're well into experimental aviation with this project.
That's true. It's highly experimental.
Highly experimental. It's so cool.
Right. Are we having fun yet? No, we're having a lot of
Uh,
fun.
but you're doing it on type certificated aircraft. That's the beauty of it.
Well, but they're not on the aircraft. That's why we can
Right.
get away with doing it. If they're when they're
Yeah.
on the aircraft, then we have to deal with the friendlies, and that's much more challenging. And that's why I think if this kind of stuff winds up in the cockpit, which I really hope it does, the first cockpits it's going to wind up in is going to be EAB cockpits for sure.
Mm-hmm. Donald wonders why sort by airframe instead of engine. His is a Cessna 182, for example.
Well, I mean, it, it's an airframe and engine combination, and you're right in a sense that the majority of the sensor data we're looking at is engine related sensor data, but not all of it. I mean, we're looking at air data, we're looking at uh, GPS data. There's a fair amount of stuff that is going into these observations that isn't directly engine related, but probably the majority of the sensors are engine related. And but again, the idea is to create a fairly well-defined blob, and the best way to do that is to train it on a set of aircraft that we know are all very similar.
David just wonders, how do you actually get the data?
You know, people upload it to us. I mean, we've been. I think we started doing this in 2010 or something like that, and we've got a platform called Savvy Analysis, and it's an omnilingual platform in the sense that it has parsers for virtually every make and model of both certificated and experimental engine monitor. So we can accept data from anything, and we can figure out what kind of box it came out of, and we know how to parse that data, and it all gets normalized into a homogeneous data model, and then it gets plotted in graphs and stuff, and it's stored away in a big giant database. It's all running on Amazon Web Services servers in the cloud. But it's
Mark,
uploaded via via website.
mm-hmm. Not automatic yet, right?
No, I mean that's another big thing that we're working on, and we're looking for a good telemetry solution. Um, that's an area where we would like very much to work with Dynon, for example, on a telemetry solution where the box in the cockpit can automatically transfer data to the cloud. Most of the Dynon boxes are Bluetooth enabled now, and so what we would like to do is develop a, like an app that'll run on an iPhone or iPad, and will grab data from the cockpit via Bluetooth and transmit it into the cellular network, into the cloud. The data from a flight, although there's a lot of observations, it's really a very small amount of data in terms of the way we think of data that can be sent over 5G or something like that. It's not a lot of data. It wouldn't require, it would not be very difficult to transfer it by telemetry if we can just get the software and hardware in place to do that.
Joe had wondered, is this something that the airlines are already doing?
The generalized anomaly detection, I suspect Boeing is probably doing a lot of that. It's been a few years since I visited the Boeing data command center that they have at their facility right by Centennial Airport in Denver. And so I'm not totally up to date on what they're doing, but they do some very, very, very sophisticated predictive analytics, and I suspect that they're doing this sort of generalized anomaly detection on 787s and that sort of thing.
John wonders, when engine monitor data is uploaded to Savvy, is it kept on file with that specific N number in addition to being added to a more general database?
Yeah, the data is all identified by the particular aircraft.
Okay. And follow up from John.
We don't use that information. We don't use the identity of the aircraft when we're training a model like this, but it's in the database. And you said there's a follow-up question?
Yeah, John is wondering, should I, as a Savvy maintenance client, be uploading all my engine data periodically to Savvy, even though I don't suspect any problems?
Absolutely, absolutely. If for no other reason, that if you upload the data regularly, you get a whole bunch of stuff from us that you won't get if you don't. You get periodic what we call report cards, which are graphical reports that show how your various aspects of the data that you've uploaded compare with all of the other aircraft of the same type that we have in our system, so that it sort of grades your aircraft on the curve. We provide trend analysis reports where we look for statistically significant trends in things like well pressure and that sort of thing, and we'll alert you if there's some statistically significant trend that you should be aware of. And then there's the FEVA failing exhaust valve analytics that we're doing, where we send you periodically reports of exhaust valve failure risk scores that prompt you to go do a borescope inspection if the data seems to indicate that a cylinder is at risk for having a burned exhaust valve or a failing exhaust valve that's starting to fail. So there are a lot of really good reasons to upload the data, on a regular basis, for sure. And frankly, aircraft owners are terrible about doing that, which is why we would really like to have an automated telemetry solution, so that it doesn't, require pilot interaction to extract the data from the aircraft and upload it to the cloud. We would love to have that be an automated function, but we haven't found the right solution yet. And Savvy is not a hardware company, and we don't want to really get in the hardware business. So the only way we're going to accomplish this is to partner with hardware people. And one of the companies who we really like to work with is Dynon. We've talked to them quite a bit, and we're hopeful that we'll be able to get something off the ground with them.
Joe asks, do you anticipate that eventually the data will show what is causing the anomalies?
I guess I'd have to say the answer to that is yes. That's not an objective of Project Gadfly specifically. We're not trying to diagnose with Gadfly. We're just trying to flag flights that somebody ought to take a look at because they look anomalous. But I don't think there's any question that the predictive analytics is going to expand greatly over time, and that more and more of the problem diagnosis will be done, by computer analysis of sensors as opposed to mechanics attacking the aircraft with tools. And I think that will be a very, very good thing. And that's certainly what's going on in the airlines. We're quite far behind the airlines in general aviation, but Savvy is dedicated to moving that forward, the whole predictive analytics thing. And we're at a bit of a disadvantage compared to the airlines because our aircraft nowadays are not riddled with sensors in the way that a modern airliner is. A modern airliner has thousands of sensors. Pretty much everything that can be measured has a sensor on it. And there's massive amounts of data that an aircraft like a 787 captures. Most of it is telemetered in real time to Boeing, and they have a massive data center that they work with. GA is in a much more primitive state. There's a significant portion of the fleet that really isn't instrumented at all. I think more than half the fleet have some sort of a digital engine monitor. But we certainly don't have the amount of sensor data that the air carriers have. But it's moving in the right direction, and we want to take it as far as we can, given what the current state of the hardware is. And over time, the airplanes get more and more electronic and more glass, and we'll naturally have more and more sensors. It's definitely been moving that way, and I think that's pretty exciting.
Bob asks, my Dynon defaulted to 4 samples per second, which I uploaded to Savvy. Is this high rate useful or overkill?
It's not useful to us, and in fact, if you do upload data like that, one of the first things that our platform does is it downsamples it to one, to 1 sample per second. It's not useful to us to have a higher sample rate than that. But various makes and models of engine monitors have different sample rates. So ones that have very high sample rates, our software downsamples it to 1 per second, which is about as fine a granularity as we really can use.
Robert says, I've been told that adding an engine monitor on my 172 is overkill.
Who told you that?
Well, apparently his IA was discouraging him from looking at a JPI 830, and he's had a very difficult time trying to find somebody to install the Garmin 530 interface to the 830 to make it useful for fuel flow data.
Well, I don't know. First of all, don't listen to that IA. There are a lot of graybeard IAs out there that don't believe in this stuff, but it's digital engine monitor is worth its weight in gold in terms of diagnostic data, and it virtually always will pay for itself. The first time you can use the engine monitor to pinpoint a problem as opposed to, having somebody, start disassembling the engine hoping to get lucky, which is the way it's traditionally been done. The thing will pay for itself very quickly. The 830 is a very good unit. Interfacing it to the Garmin 530 is basically trivial. It's one serial connection, basically 2 wires. Why having a problem getting them interfaced is beyond me, because it's really quite trivial to do that.
Bill asks, how useful is an engine monitor with a carbureted engine?
Extremely useful. What does the carburetor have to do with it? If it has pistons and cylinders and spark plugs, then it ought to have an engine monitor. Doesn't matter whether it's injected or whether it's carbureted.
Corey wonders, is Gadfly going to be a standard feature for Savvy Aviation customers, or is it a premium fee service?
No, we've not had any discussions about charging any kind of a premium for it. This is going to be a standard part of what we offer to all of our clients: Savvy Analysis Pro clients, Savvy QA clients, Savvy MX clients. All will if their aircraft is a make and model that for which we have a a Gadfly anomaly detection model, then their data will be scanned by Gadfly, and we don't have any intentions of charging extra for this.
David wonders, is the objective to typify normal configuration performance and allow the pilot owner to have their aircraft analyzed by the maintenance shop, or to enable big data monitoring of all aircraft?
Boy, I did not understand that question, Tim. I couldn't make sense of that, so I'm not sure how to answer it.
Okay. Joe wonders, what effect will unleaded fuel have on the data?
None. Unleaded fuel is going to be a very good thing, I think, for GA, but it's not going to have any effect on the data.
Mm-hmm. Mark wonders, did you contact the owner in the example to see what ultimately happened?
Oh, for sure. Without question. No, they bore scoped that cylinder, and the piston was a mess, and the cylinder had to come off and get reworked. That was a pretty violent event.
Chris wonders, what sample rate would be required to discover a prop strike?
Prop strike would be pretty easy. I'm joking about this, but if you want to discover a prop strike, if you have an RPM sensor and you suddenly see it go to 0, that's going to be a pretty good indication of a prop strike. Again, it depends on how many sensors the aircraft has. All SR-22s, have RPM, manifold pressure, fuel flow, pretty much everything that is on a cockpit readable instrument is captured in the data. And I've looked at data from a prop strike, and you can see exactly where the prop strike happened because there's a precipitous drop in RPM. So it's pretty easy to do. If the engine didn't have a sensor on RPM, then you would have to deduce it from other things. Like, for example, a fuel flow would suddenly drop because the fuel pump would stop rotating after the prop strike. So
Michael was
you know, you don't really need an anomaly detection algorithm to tell you you had a prop strike. I think everybody, that's pretty obvious.
hmm,
Just sitting in the cockpit that you had a prop strike. So
Michael was wondering, the example that you presented, the piston failure due to the runaway, is an extreme one that a basic monitor could have prevented if the pilot received a warning and took action. Do you have a less extreme example where Gadfly could have helped detect and prevent some harm or signal maintenance is needed?
oh, sure. I mean, we see all sorts of variations of this sort of thing. If we're talking about an abnormal combustion event, um, if it's, you know, moderate detonation, you can wind up seeing a CHT rise over a fairly extended period of time, instead of doing it suddenly, like the one in the particular flight that I showed. That's why I think that flight was most likely a pre-ignition situation, because the rate of CHT rise was very rapid. My kind of personal rule of thumb is if CHT rises more than 1 degree per second, it's probably a pre-ignition event, because it's hard to heat a cylinder head up that quickly. It takes something pretty violent to do that. But you know, in a previous webinar, I forget which one, I think I had some slides that showed this was another SR-22. It was flying over Florida, and it had detonation develop in one of its cylinders, and the CHT majestically rose over a period of, I don't know, 12 or 13 minutes. Wound up hitting red line, which was 460 degrees, and the cylinder head separated from the from the barrel at that point. And the pilot had, you know, 13 minutes to notice that something was wrong, and this is a SR-22, so it's, you know, it's wall to wall glass, all sorts of good instrumentation in there, and he just was blithely flying over Florida and wasn't paying any attention, and suddenly had a cylinder separate on him. But he had a long time to detect it. He just wasn't looking.
Gerald wonders, would this data be useful in determining when it's time for an overhaul?
No, probably not. Um, you know, I have some pretty strong feelings about what sorts of things justify overhauling an engine. I've done a webinar on that subject about when to overhaul. But the things that would warrant an overhaul aren't anything that shows up in engine monitor data, because engine monitor data is looking at the hot section of the engine, if you will. It's looking at what's going on inside the cylinders. And we don't overhaul engines because of anything that's going on inside the cylinders. If something really bad goes on inside the cylinder, like the one we looked at, we change the cylinder. We don't tear down the engine. So the only reason to tear down an engine, if something bad is going on in the bottom end of the engine, inside the crankcase, that can't be resolved without splitting the case. And that's not the sort of thing that there are any sensors that will detect. That's the sort of thing we cut open oil filters to look at, and we send oil samples out to laboratories and stuff like that. But it's not anything that we can look at with sensors, because we don't have any sensors down there in the bottom end of the engine.
Chris wonders, do most engine monitors include GPS to timestamp the data they collect?
Some do, some don't. It just depends. You know, an awful lot of the fleet are still equipped with these old, like JPI 700s that really have not much more going into them besides CHT and EGT. The more modern ones, tend to capture GPS data. They will normally have fuel flow and air data and lots of other good stuff. And the more sensors that we can capture, the more we can do with it. And again, that's one of the reasons that we're using the SR-22 as the kind of beta test airplane for this Gadfly project, because they tend to be quite well instrumented.
Milton says, I'm transitioning from an EDM 700 to an EDM 900. Should I submit the final 700 data before the new install?
Probably, yeah.
Steve wonders, are there any specific flight steps or flight techniques you require in flight to get the necessary analysis data?
Well, I wouldn't phrase it that way, but we do have what we call our flight test profile, which we like our data analysis clients to fly a couple times a year, which involves doing things like a very slow in-flight mag check and some sweeps of the mixture control and so on. Takes about 15 or 20 minutes. You could do it on a normal cross-country flight. Doesn't require doing a special flight just for this. But it captures an unusually rich data stream and lets us do a lot of good diagnostic work that would be hard otherwise. So we like to see our clients fly the flight test profile a few times a year, and particularly we like to see them fly it, right before an annual inspection comes up, because we want to take a really close look at the data and see if there's anything going on that ought to be addressed during the annual. But it's not mandatory to do that. We look at lots and lots of flights that aren't test flights like that, but we do publish this flight test profile, which helps us capture a diagnostically rich data stream.
Jeff wonders, when a cylinder is measured during annual inspection and we have low compression results, what kind of engine data would you expect to see?
I would expect to see absolutely normal data. The compression readings, I've done some webinars on this too. Compression is not a particularly meaningful figure. It's a very old, rather archaic test that unfortunately got written into the regulations. So as an IA, I'm required to do it, but it isn't particularly interesting. The signal to noise ratio on compression tests is very low, and compression tends to vary all over the place from one measurement to the next and from one year to the next. And it'll get worse one year and it'll get better the next year. And you know that the cylinder didn't get sick and then heal itself. It doesn't work that way. It's the test that's bad. So, our emphasis in terms of determining cylinder condition is to use the borescope as the gold standard for determining what's going on inside a cylinder. The compression test is one that I would relegate to the scrap heap if it wasn't written right into the regulations that we're required to do it. So we're required to do it, and we do it, but we don't give a lot of credence to compression readings because the test is very flawed. It's not very repeatable. It depends heavily on mechanic technique. Cold compression readings and hot compression readings are kind of drastically different. So I'm not a big fan of compression tests. We do them because we're required to do them, but we don't like them.
John wonders, What engine monitor would you suggest for a steam gauge Christian Eagle to bring it into the modern digital world?
Well, I mean, depends on how much money you want to throw at it. JPI EDM 730 or 830 is a nice unit. I wouldn't go to one of the LED bar graph gauges at this point. I would get something with with a color flat panel display. But if you just want a supplementary instrument, something like a JPI EDM 830 is a good choice, or a Electronics International CGR30P is a very nice instrument. The a little more money, the Garmin GI 275 EIS is very nice. And then if you want to go a step further, you can get one of these primary instrument replacement units that let you rip out a whole bunch of your old steam gauges and use the new unit for that. It's more expensive. One of the advantages of it is it captures a lot more data because you've got a whole bunch more sensors connected to it. But it's really a question of what your budget is. But for an entry level unit, a JPI 730 or 830 or a Electronics International CGR30P are a good place to start.
All right, Mike. Well, hey, great presentation. Looks like we had a little over 500 people logged in tonight. Why don't you take a moment and
500 geeks, huh?
500 geeks, yeah. Take a moment and share your closing thoughts with all us geeks.
Okay, well, I appreciate the geeks hanging in there. Just very quickly, if you'd like to get on our email list for our monthly newsletter and occasional interesting maintenance stories and stuff that we send out, and announcements of presentations and so on that I'm going to make, the easiest way to do that is to text the word savvy, SAVVY, to 33777, and a little text bot will ask you for your email address and add you to our mailing list. My books are available on Amazon, the EAA bookstore. They just stocked up again. I was not glad to see that. The Aircraft Spruce sells them. My manifesto book is also available as an audio book, and we're right now in the process of hoping to have it done by the end of the year, putting the engines book, which is a big 500-page book, in audiobook format. But at any rate, the books are available in soft cover right now, and the manifesto book is available as an audio book, and the engines book will hopefully soon be available as an audio book. I'm an audiobook freak. I'm always listening to an audiobook on my phone, so I wanted to do that. Figure there's some more of those out there. The Ask the A&Ps podcast that I do with my colleagues Colleen Sterling and Paul New. Boy, that thing has been going through the roof. We've doubled our listenership in the last year, and we're about to be the highest rated of all of the podcasts that AOPA is producing, which is really amazing because we've only been doing this for a little over a year. But at any rate, it's a maintenance oriented call-in show, and we answer questions and have a lot of fun. It's kind of modeled after the old NPR car talk program, except it's for airplanes instead of cars. And if you'd like to participate in the show, if you'd like to listen to it, it's available everywhere you can get podcasts, and we're not actually doing it in video. We've got a YouTube version, so you can actually see us do silly things instead of just hearing us. But if you have a question you'd like to participate in the show, email our producer Ian Twombly at podcasts@aopa.org, and he'll schedule you and get you on the show. And finally, the next 3 webinars that I have coming up, first Wednesday of every month, I guess the next webinar, it's going to be next year. January webinar called Systems Awareness. It's actually about something we were starting to talk about in the Q&A session tonight, about paying attention to what the gauges are telling you, so that you're aware if you have problems and you don't let them sneak up on you. Should be kind of an interesting webinar. February, it's entitled "Obsessed with EGT," and talks about how people are hung up on EGT and they really shouldn't be, and why I do not recommend using EGT as a leaning reference and all sorts of stuff like that. But anyway, it's going to be focused on understanding what EGT is good for and what it's not good for and what it means and so on. And then the March webinar is titled "A Matter of Trust," and it kind of has to do with annual inspections and whether an IA has to verify every aspect of airworthiness himself, or whether he can trust other IAs who have made logbook entries that say something is done. And there was an interesting little journey that we had with one of our clients, where an IA wanted to tear down his engine in order to verify that a particular AD had been complied with, and we wound up preventing that from happening. But it opened up a whole bunch of interesting questions with regard to regulations and what's required of an IA and so on. So I'm going to be talking about that in the March webinar. And I guess that's all I have, Tim, until next year.
Well, thank you so much, Mike, for very interesting and just groundbreaking presentation. Love the work you're doing there. Many people are just thanking you, and fantastic presentation. And thank you for doing this to help us. And looking forward to next year, sir. We'll see you then on January 4th, Systems Awareness. Thank you so much, Mike. To everybody who tuned in, thank you for joining us, everybody. Have a great night.
Thanks. Good night, everybody.